llama.cpp just gained a model where one control token can change which embedded adapter handles every following token. The shipped demo runs the same prompt twice, placing a control token before the assistant produces a visibly different specialized output. That makes model behavior routable inside local inference, without pretending this is a general adapter system or a finished multi-turn solution. Once an adapter fires within a sequence, the faithful router cannot return to base until that sequence ends. So the real story isn't merely model support. It's how llama.cpp converted, loaded, routed, and constrained this unusual architecture. Pull request 25107 merged 48 commits into llama.cpp master on August 10th, then appeared in release B10342. The release calls Granite-Switch a dense, all-attention Granite 4.1 model with multiple embedded LoRA adapters selected per token. The pull request explicitly says the model is dense, not mixture of experts, even though matrix selection machinery chooses one adapter slot. These aren't separately attached runtime files in this implementation. Conversion stacks the adapters into tensors stored with the GGUF model. The converter also adds a zero-filled base slot, so ordinary tokens can select an exact zero adapter delta. The release lists a Granite-Switch model converter that emits switch metadata and stacks adapter A and B tensors for each projection. llama.cpp added architecture registration, model loading, graph input handling, and a dedicated Granite-Switch execution graph for inference. Reviewers discussed refactoring the existing adapter infrastructure, but the merged path kept specialized logic centered on Granite-Switch. To understand why that choice works, follow a token from prompt text to adapter ID, matrix selection, and added model delta. Here, a LoRA adapter is a compact pair of matrices that adds a learned delta to selected model projections. The release identifies 7 adapter injection sites: query, key, value, output, gate, up, and down projections. Each injection site needs an A and B tensor, producing 14 stacked tensors that hold all adapter slots. For every token, Granite-Switch selects exactly one adapter slot, rather than blending several adapter deltas together. A designated control token maps to an adapter slot. Ordinary tokens map to the base slot unless an earlier switch remains active. The graph input maps control tokens to substitute token IDs while separately preserving their adapter selection signal. The proof of concept stored one mutable adapter index on the CPU, shared globally across processing batches. With multiple sequences, the last writer could leak one sequence's adapter into another, making concurrent requests unsafe. The merged implementation replaces that global index with single-head causal router attention computed inside the model graph. The router is causal. Each token can read routing signals from itself and earlier positions, never from future tokens. Only dimension 0 carries router information. Query is 1, key marks control presence, and value carries the adapter slot. Causal softmax emphasizes the visible control token, then its value is rounded and clamped into a valid adapter index. Think of Granite-Switch as one dense model carrying a built-in tool belt, with a control token choosing one attachment per token. The recovered adapter ID travels through the graph, so each layer can select matching LoRA matrices for that token. Each LoRA tensor stacks adapter slots along another dimension, letting matrix selection retrieve the chosen slice directly. llama.cpp uses ggml.multimatid over those stacked tensors, directly selecting the matrix ID assigned to each token. When the active slot is 0, the selected A and B slices are zero-filled, so the adapter contribution remains exactly 0. When another slot is active, its A and B slices produce a learned delta that is added to the base projection. That switched delta is added at query, key, value, output, gate, up, and down projections throughout the model. The router stores its key and value signals in an extra layer of the model's KV cache for each sequence, and the implementation allocates that router cache layer while keeping the regular decoder layer count and loading path unchanged. Router keys contain literal routing magnitudes, so the release says their cache layer is excluded from key shift rotary processing. Because selection lives in per-sequence cache state, concurrent requests no longer share one last writer adapter index. A merged commit asserts token input to avoid undefined behavior, while raw embedding input is explicitly left as a TODO. The full chain is control token, router attention, adapter ID, stacked matrix selection, then additive deltas across the dense model. The release says the 3 billion checkpoint converted into 842 tensors with stacked dimension 13 and generated through base and control token paths. The Mac demo used the same prompt twice, adding only a control token before the assistant turn to expose switching. In the reported answerability demo, the control token path produced unanswerable, while the paired base run used the same prompt. In the query rewrite demo, the switched path returned a rewritten question JSON object, again from the paired prompt setup. Those runs demonstrate functional switching. The verified packet provides no speed, memory, quality, or quantized performance comparison. The pull request accumulated 48 commits, review discussion, correctness fixes, approvals, and a final merge into master. Review comments questioned shared code hacks, adapter extensibility, and repurposing the next token layer count, even as the change gained approval. We know switching runs end-to-end and isolates concurrent sequences. We don't yet know its broader performance envelope. The router gain is flat rather than recency biased, so an earlier control token remains visible throughout the sequence. Within one sequence, there is no mechanism to revert from an activated adapter back to the 0 base slot. If a client continues 1 KV cache across turns, the adapter can remain active into the next conversation turn. The documented workaround is to start a fresh sequence for each served turn when base behavior must reset. The release describes this single switch contract as identical to the Hugging Face and VLLM implementations, not a llama.cpp only surprise. That contract naturally suits serving, where each request is a fresh sequence. Persistent chat clients must manage resets deliberately. Implementation notes repurpose the next token layer count to reserve the router layer, despite there being no MTP head. One reviewer warned that changing this field could create unintended side effects because other code paths also use it. The change is real and merged, but the source packet supports one model architecture, one 3 billion conversion example, and functional demos. For local builders, the packet cannot answer whether this is faster, smaller, or better than loading another specialized model. The answer depends less on headline novelty and more on whether your application can honor token control and sequence reset rules. Experiment if you need one local model to expose distinct behaviors, selected by explicit tokens, inside fresh request sequences. Be cautious if your client keeps 1 KV cache across turns or expects adapters to switch off mid-conversation. Plan around token inputs, verified GGUF conversion, and the model-specific graph. Raw embedding support remains explicitly unfinished. Granite-Switch support is a credible architecture milestone, not yet evidence that adapter switching improves everyday local AI performance. Watch for raw embedding support, a safer router layer integration, reset behavior, and real speed, memory, and quality measurements. If you build local agents, follow the implementation details, not just the model headline, and subscribe for the next verified update.